Hello everyone. All right, welcome back. So today we actually have several different things to talk about. First of all, we haven't quite yet finished there's I think there are several slides in the advanced graph algorithm about the single source shortest path problem. Yeah, we will go through that first. So basically, it's about a special case of finding the single source shortest path in a directional acyclic graph, which is DAG. Okay, and it's a more efficient algorithm because the input is acyclic, right? Which excludes the possibility there could be negative, there could be cycles in the graph. So it saves more time as compared to Bellman-Ford algorithm. Okay, and it's also quite a little bit related to the topological sorts. Actually, it's quite related to the topological sorts algorithm in a elementary graph algorithms. Right, so that is the first part we're gonna cover today, and then we actually have a new lecture, but it is a pretty short one, which is our last lecture on the NP completeness. I think I have already uploaded to Canvas. Okay, so it's module 10. NP completeness, and you can go ahead and download it. So that is the one we will cover for the second part, and lastly we will go through the final review. Okay, we will talk about what will be covered, what questions will there be in the final exam, and what is the. I will also give some suggestions to for you to prepare the exam, okay? Just like what we did for reviewing the first and second midterm exams. Alrighty, let's get started. I will start sharing the slides for the graph algorithm first. There we go. Okay. I need to pin my video here. All right. So yeah, let's look about this. So maybe we should have a little review of what Bellman-Ford algorithm does. All right, let's just use this slide. Okay, so we should also have another one. Yeah, let's use this one. So we know that the algorithm, the Bellman-Ford algorithm, is not a super efficient one because it has two nested for loops, basically, right? It's two nested for loops, and the outer loop have v-1 iterations, while each of the inner for loop goes through the whole set of edges, right? So it's basically the total time is at this big O of v times e, yeah, which is relatively a quadratic running time algorithm, and you can say that it's not that efficient algorithm, right? Because it's basically it doesn't place very strong constraints on the input graph. It doesn't require that the input graph shouldn't contain any cycles, shouldn't contain negative weights, and so on, right? So these algorithms have to go through, have to have sufficient amount of relaxations, the basic operation executed. So at the core of the algorithm, it is the execution of the relax procedure, right? It has to execute this line of code for enough time of for sufficient amount of times, right? So otherwise, the attributes listed for each vertex will not be the theoretical, theoretical minimal value. That is the shortest shortest path distance, right? So that is Bellman-Ford, and the inputs that we have for now for the DAG is that now we have some constraints on it. It's actually a directed graph, and it's also acyclic, which means that, okay, there is no, we know for sure that there's no cycles in it. Okay, so for this particular type of graph, what we can do is actually to utilize the topological sort algorithm that we have defined in the using the depth first search, right? In topological sort, that's what we already know. We just use run DFS once and record all the finishing time, and then we basically take the vertex out after it is finished and place all the vertices in such an order, right? In the linked list, and that will be the result of the topological sort. Okay, so here we will utilize the topological sort of all the vertices. Okay, and that will save us time so that we can compute the single source shortest path within this amount of time, which is big theta of v plus e, right? Which basically turn it into a linear running time algorithm, which is way faster than this big O of v times e. Okay. All right, let's go to more of the details. Okay. Yeah. So one property about a DAG is that because there's no cycles, that's something we know for sure. So the shortest paths are always defined, right? Because there's no cycles. There's no such a possibility that we go through the same edge for multiple times. So for each vertex, the shortest paths are always defined. Okay. So what we need to do is simply to first run a topological sort on the DAG, right? And we know that the result of a topological sort is the reordering of all the vertices. Okay, so that all the edges, they are always pointing from left to the right within the sorted vertices, right? There's no edges pointing backwards. Okay, so the property of the topological sorted result is that if there is a path from vertex u to v, then within the sorted results, the u must come before the vertex v in the topological sort results. Okay, so upon these results, we can simply make just one pass over all the vertices in the topological sorted order. And then as we process each vertex, we will call the relax procedure on each edge that leaves the current vertex just for once. Okay, and we are done. Okay, so it's basically just one more step than a topological sort. Okay, after all the vertices are sorted, we follow that sorted order and we examine each vertex. And for each vertex, there will be some edges that leaves the current one, right? Or there will be none, right? So if there's any edges that leave the current vertex, we will call the relax edge. We will call the relax procedure on that edge. Okay. And after we have gone through all the vertices, then we're done with the single source shortest path algorithm. Okay. So if we are given the code like this, let's take a look. Take some look at it. Okay. So we will directly use the topological sorts procedure. So we are not gonna redefine it, right? So in line 1, we will simply call the topological sort, okay? And it also takes big theta of v plus e time. And in line 2, that's something we have to do. We need to initialize all the vertices, right? By assigning the d attribute and the pi attribute accordingly. So the next for loop, so it looks like a nested for loop, right? But it's not the same nested for loop as used in Bellman-Ford, okay? So for the first one, it's just go through all the vertices in topologically sorted order, right? And then the next one is just to go through all the adjacent vertices for the current vertex, okay? And we relax all the edges that start from the current vertex and points to the adjacent vertex, okay? So that edge is the one that leaves the current vertex. So this type of code structure is something we have already analyzed several times, no matter it's in topological sorts or other algorithms. So it's basically the outer for loop iterates over all the vertices, while the inner for loop will relax each edge exactly once. Okay, so there will be no repeated relaxations. So we can say that the total running time should be big theta of v plus e. Okay, I think this conclusion is quite straightforward. All right, so we have an example here. Let's go through it quickly. All right, we have the input like this, and it's actually a DAG. It is directional, while there's no cycles in it. Okay, so if you examine it yourself, you will basically find that there should be no cycles that points back to the points back from the descendants to the ancestor vertices. Okay, so we will basically first call the topological sort, which gives us a reordering of all the vertices, and then we initialize all the d's with the correct values, which is either infinity or 0, right? Because 0 is where the source is at, right? So for the source, it's initialized to 0, okay? All right, so, and then we will go through all the vertices. Okay, let's see the chat. So I see your comments. So just because of the trouble, so that's. So, yeah, that's a good point. I don't think there are algorithms that are, faster than a linear running time if you want to go through, if you want to have a direct traversal of the graph. Okay, that's determined by the nature of the or by the goal of the algorithm, right? If we don't want to lose any information, if we don't want to miss any edges or vertices, I think basically we have to spend that necessary amount of time. Okay. Okay. So let's carry on with the example. Okay. So the algorithm tells us that we need to basically go from left to right, right, in the sorted results. So R in this time will be the first one, right? We have to relax 2 edges, right? Because there are 2 edges that leaves the R vertex, right? Which is RS and R2T. So, and then we will call the relax on the edge. And what relax does is to compare like 2 quantities, right? The first one is the v dot d, and the second one is u dot d plus the edges weights. Okay, so in this case, the u is the source vertex R here, right? And the v could be S and it could be T. So we just follow the relax algorithm, and we should get the results. Okay, so after relax, we have the value of t updated to 2. Okay, and so no, it's there in the first pass. There's no change. Okay, because the initial values for r dot d is infinity. So these if statements will never be satisfied when we relax rs or rt, right? So it will basically do nothing on this algorithm on the first iteration. So in the next iteration, we will go to the s, right? It will basically relax 2 edges, right, from s to t and s to x, right? And this time, since the d of s is well defined, so we need to follow the code in the relax and update the d's for t and x accordingly. Okay, so we'll simply do that sequentially for each vertex that we meet, that we come across within this topological sorted order. Okay, and after the last one is achieved, is seen, we basically have done with the algorithm, and we have see that all the d attributes in the vertices have been correctly assigned. That is, the single source shortest path from the source to each destination vertex. Okay, so there's one special vertex, which is r, right? It's assigned with the infinity, right? So that is because r is not reachable from s, right? Since the graph is directional, and the edge from r to s does not necessarily mean that you can go from s to r. That's 2 different edges. So in this case, r is not reachable from s, so the distance is not well defined. The distance for r is not defined. It's not a finite value. Okay. All right. That is a complete example for the single source shortest path problem. So are there any questions about this algorithm? Okay. Okay, so we will let me stop the recording, okay?